In this video, I want to introduce you to the concept of transformations, in particular, matrix transformations. Now, the rest of this course will basically be about transformations. Okay? And we have done a little bit of this already, as you'll see. First, I want to just define a transformation, not necessarily a matrix transformation. So given two vector spaces, V and W, a transformation, which we'll call T, from V to W, is a mapping that takes each element of V and assigns it to an element of W. Think about functions, right? We have functions we usually think of as the input of real numbers, and it gives you a real number as an output. That is a function. It's a transformation from R1 to R1. But there's other things too that are transformations. Think about taking a derivative, right? That is, you take a function in and you get another function out. That's a transformation from the vector space of functions to the vector space of functions. You could think of determinants, right? Determinants take a matrix, a square matrix in and give you a number out. So that would be a transformation from n by n matrices, and it returns a real number. So matrices, square matrices to real numbers. Okay. These are all examples of transformations. Okay. The notation that we're going to use it looks like function notation. First, we start with the name of the function, t. In parentheses, you put the input, that is something coming from the vector space V, and then that's going to be equal to whatever it's being assigned to in W. Like functions, these transformations give you only one output. For each input, you get only one output. Now, you might get the same output from several different inputs, that's okay, but each one thing in is only giving you one thing out. Okay. Now, a few other definitions that go along with this. The space that you're starting from is called the domain space, and the space that you're ending up in is called the codomain. So the domain and the codomain. You might have thought I was going to say the range. Well, we do use the word range as well, but the range is just the part of W that actually gets hit. Right? So, for instance, if you think about the transformation, or function, if you will, right? F of x equals x squared, so taking real numbers to real numbers. The domain and the codomain are both R1, but the range is only the non-negative real numbers, right? Because when you square a real number, you're never going to get a negative. So the codomain would be all of the reals, and the range would just be the non-negative part. The picture drawn generally looks like this, where you've got this vector space V over here, and you've got this vector space W over here. The arrow is labeled T because that's the transformation that's taking stuff from here to there. And a typical element here, V, gets mapped to W, which is equal to T of V over there, the blue dot. And I have this sort of smaller ellipse inside here because maybe not all of W gets hit. But what does get hit is called the range of that transformation. One more word that we use, if the range space and if the domain and the codomain are the same, then this is called an operator. So the functions that we generally work with, real numbers to real numbers, technically are operators. The derivative is an operator. It takes a function in, it gives a function out. The determinant is not an operator because it's starting in the space of square matrices and it's ending in the space of real numbers. So that's just a transformation. It's not an operator. Now, in particular, in this section, we want to talk about matrix transformations. And a matrix transformation is based off of having a matrix. So if I'm given an m by n matrix A, we define this transformation. So the notation is this is transformation based on the matrix A, and it goes from Rn to Rm. Remember, this is an m by n matrix, where T of A of some input is just multiply by that input. And for some reason, I'm using x here, but I used v's here. So this is supposed to be a vector v, I guess. whatever. And we would denote it here just as take the vector x, which is v1, v2 up to vn, multiply by this matrix, and you get the output w1, w2 up to wm, right? We've been doing this all quarter, or almost all quarter, right? That is, w1 is going to essentially be the dot product of the first row with that vector x or v, whatever I'm calling it. W2 will be the dot product of the second row with that vector, and then W3, the third row, dotted with that vector, and so on, all the way down to Wm being the mth row dotted with this vector. Right? Because this is not necessarily square, the number of rows and columns are different, so there's m rows and n columns, so this has to have n entries in it, so that's why I'm starting in Rn, but then I dot it with these n things in each row, but I only have m rows, so the output is just in Rm. Okay. I say that we've done this already because we've been doing change of basis, using matrices, transition matrices, to go from coordinates with respect to one basis to coordinates with respect to another. Now notice that in those the matrix was square. Right? They were n by n. So this was Rn to Rn, and this you would even think of as an operator. Right? The change of coordinate transformation is an operator, taking Rn to itself. And it was achieved by multiplying by a matrix. And we would, we spent a little bit of time figuring out how to get those matrices. But we can do all sorts of different things by just multiplying by a matrix. One of the things that I really want to emphasize here is that when people first learn about matrices, they learn about them in the context of, hey, we're solving systems of equations. And for each system, there's the augmented matrix that you put in a reduced row echelon form to help you find the solutions, right? But then we switch that up a little bit and say, well, what if we just look at the coefficients? Make a matrix out of just the coefficients, and then we can actually use some matrix arithmetic to solve the equations in another way, right? Find the multiplicative inverse and multiply both sides and solve it without doing the reduced row echelon form. But still, that's all in the context of systems of equations. But matrices can be used for so many other things, right? That you get in the habit of thinking, oh, this is just about systems. Well, no, it could be transformations, or it could be other things. Whatever you find them useful for, you can use them. In this case, transformations, it's really nice to be able to take a vector in one vector space, multiply it by a matrix, and now you're sitting in some other vector space. And we can start looking at the properties of those things and the usefulness of those transformations. There are two basic questions here that you'll see in the homework. One is, if you're given a vector v in Rn, can you find t sub a of v? Can you actually apply the transformation to this vector? Well, I hope you can, because all you have to do is multiply the vector times whatever matrix A is. And at this point in the course, you really ought to be able to multiply a vector times a matrix. Likewise, we could go the other way. We could say, hey, suppose I've got a vector w in Rm. I want to find a vector v in Rn so that Ta of v is equal to w. Can you find space? So for instance, if I said 49, can you find a number that under the function f of x equals x squared, gives me 49? You could say, yeah, I think I can find that. Now that's not a matrix transformation, as it turns out, but it's the idea of, you given the result, can you find the thing it starts from? Well, the thing is, how do you apply the transformation Ta to the vector v? Well, you're just multiplying by the matrix A. So the question is, if you know W and you know A, can you find V? Well, this is precisely solving systems of equations, right? This is what we've been doing all quarter. So again, I hope that you are able to do that without me necessarily showing you a example at this point. In the next video, I want to take a look at the properties of these matrix transformations and linear transformations in general.